in the last section we looked at how, some of the basic trig forms, essentially reversing those derivative formulas we already knew. In this section, we're going to look at other trig forms, and in particular, we're going to look at, we're going to basically kind of learn a strategy for how to approach integrals that are in one of these forms, like powers of sines and cosines, or powers of secants and tans. And I should mention that the strategy that works with powers of secants and tans would also work with powers of cosecants and cotans. So we're going to start with a couple simpler ones that we already know how to do with a U substitution. In the first one, in part A, we've got sine to the fifth x times cosine x dx. Remember that the derivative of sine is cosine. And so if we let u equal sine x, then du is cosine x dx. And this is a power rule integral. If I make the substitution, we get u to the fifth du. And that gives us 1/6 u to the sixth plus a constant. And putting our expression back in, we get 1/6 sine to the sixth of x plus a constant. In this next one, I'm going to start actually just by doing a simple-ish rewrite. Well, it is a simple rewrite. It doesn't always occur to us to do this, but we have this secant to the fourth. That means we've got 4 factors of secant sitting there. I'm going to peel off 1 and tack it on at the end. So I'm going to write this secant to the fourth as secant cubed x times secant x. And then we have tan x dx. And I do that because it helps me realize I've got this secant tan at the end. Secant tan is the derivative of secant. So here I'm going to let u equal secant x so that du is secant x tan x dx. And this is another power rule integral. This is the integral of u cubed du. So we get 1/4 u to the fourth plus a constant, or 1/4 secant to the fourth of x plus a constant. So we already know how to do these, right? We've seen integrals like this when we were making U substitutions with the power rule. We're going to use similar strategies, but we'll first need to use algebra and also some trig identities. So we'll find it handy to have these identities close by. We'll find it useful to use the Pythagorean identity and occasionally the half-angle identities for sine or cosine. So we are kind of breaking this down, our strategies. We're breaking this down depending on what these powers are. So we're gonna look at sines and cosines first. And so remember, up here I said, we're gonna look at scenarios where we're integrating a product that involves powers of sines and cosines. And we break it down by if we have one of those exponents being odd and positive. In these notes, I kind of break this down separately, like if the power of sine is odd and positive versus if the power of cosine is odd and positive. But the strategy between these two is basically the same. So if one of these powers is odd and positive, we're in pretty good shape. We're going to peel off a factor of that function that has the odd and positive power, throw it at the end. So here what that looks like in example 717 is that I've got this sine cubed, so I'm going to take one factor of sine and I'm going to throw it at the end. So I'm going to rewrite this as sine squared x cosine to the fourth x sine x dx. Okay. Now the whole point of throwing that factor of sine x at the end is that we're thinking that that will be our du. It seems odd that we're kind of thinking about du first before we pick u, but if we're thinking that sine is going to be our du, or a multiple of sine is going to be our du, that means we have to be thinking about u equals cosine. So if u is cosine x, du is negative sine x dx. We're off by a -1, but that's fine. We can throw that in. Now, if our u is cosine x, I want the whole rest of the integral to be written in terms of u. So we've got our du at the end with the sine x dx. And the cosine to the fourth. I'm pretty, satisfied with that because I've got that's my u. But this part, we want to write in terms of u. There's no du squared, right? So I want everything. I got a du at the end. I want the rest of the integral written in terms of u. So here's where we're actually going to use the Pythagorean identity. Pythagoras says sine squared x plus cosine squared x is equal to 1, and that means that sine squared x is equal to 1 minus cosine squared x. So I'm going to make that substitution first. So we have 1 minus cosine squared x times cosine to the fourth x times sine x dx. Now, in order to have my du, I need a factor of -1. So I'm going to throw that in, compensate on the outside. Now I'm going to make my u substitution. I've got this integral written with x's. I'm going to write it with u's. Got a negative integral. In the parentheses, we have 1 minus u squared, and then cosine to the fourth is u to the fourth. At the end, here, that's our du. Now, look what we ended up with. It's not something that's just automatically ready to integrate yet, but we have a path forward. We can use algebra to rewrite this. Let's distribute the u to the fourth. We get u to the fourth minus u to the sixth du. And this is a polynomial. It didn't end up being just a one-term power rule like those examples on the last page, but it's a similar scenario. I just have multiple terms. It's still a power rule integral. I just have multiple terms. So we can integrate this. This is simple to integrate because we know the power rule. I'm going to bring down the negative, and then this is 1/5 u to the fifth minus 1/7 u to the seventh plus a constant. I'm going to do two things right now. I'm going to distribute the negative, and I'm going to substitute in the cosine x for u. So I've got -1/5 cosine to the fifth of x plus 1/7 cosine to the seventh of x plus a constant. And that's the result. Let's try another. Now if the power of cosine is odd and positive. So it's the same thing. I'm just looking to see if one of these factors is odd and positive. I'm going to save a factor of cosine this time, because that's the odd power that I have, and throw it at the end. The whole idea behind that is that that's going to be my du. So we're right out the gate, we're thinking, okay, I'm going to let u equal sine x. So we have sine squared x times cosine to the fourth x times cosine x dx. The whole idea is that right here is our du. So we must be thinking that u equals sine x. And if u is sine x, du is just cosine x. So I'm not off by a factor of anything. Right? I've got that all set. But I want the whole thing, the rest of the integral, written in terms of sine, because that's my u, which means I got to do something about this cosine to the fourth. So again, let's use Pythagoras. Pythagoras tells us sine squared x plus cosine squared x is equal to 1, which means cosine squared x is 1 minus sine squared x. Now we don't just have cosine squared, we have cosine to the fourth, but you can use Pythagoras on any even power. So just note, look what happens if I square both sides of this equation here in the identity. If I square both sides, on the left side I get cosine to the fourth x. And on the right side I'm going to square this out. 1 minus sine squared x times 1 minus sine squared x. And if I FOIL this out, I get 1 minus 2 sine squared x plus sine to the fourth of x. And in fact, actually, I'm going to, bear with me, I could keep going with this, doing the algebra with the trig functions, but there's also another option here. So I'm just going to kind of show you how slick this can be. So cosine to the fourth is 1 minus sine squared x squared, right? And I'm going to just plug that in right now. And I'm going to make my substitution now. I could do the algebra out with leaving the sine x in, but sometimes it's easier to do the algebra just less messy if you just put the u's in first. So that's what I'm going to do here. So sine squared, I'm going to make my u substitution here. U is sine x, so sine squared x is u squared. Then we have in the parentheses 1 minus u squared, and we're squaring the parentheses. And then at the end, there's our du. I'm going to do the algebra on this just because I think it's a little bit simpler. So I got the integral of u squared times, this will be, let's see, if we expand this out, it'll be 1 minus 2u squared plus u to the fourth du. And again, it's not just a single term power rule, but this is a polynomial. I'm going to distribute this u squared on the out in front here, so I've got the integral of u squared minus 2u to the fourth plus u to the sixth. And it's still a power rule integral, it's just multiple terms. I've got a polynomial here. So this is 1/3 u cubed minus 2/5 u to the fifth plus 1/7 u to the seventh plus a constant. The integral with u's is easy to do, so the u substitution has done its job. We've integrated. Now we're going to put our expression for u back in. U is equal to sine x, so we got 1/3 sine cubed x minus 2/5 sine to the fifth x plus 1/7 sine to the seventh of x plus a constant. So we know what to do if we have an odd positive power. And by the way, if they're both odd and positive, just take your pick. Pick, one of those factors to put on the end to be your du, and then your other function, sine or cosine, will be your u. It'll work out either way. One way will give you a result that involves terms of powers of sine. One technique the other way would give you a result that involves powers of cosines, but they would be equivalent. You could show that they're equivalent using the Pythagorean identity. If we don't have any odd positive powers, then that's where the half-angle identities come in. So if all you have are even, non-negative powers, then you're going to use the half-angle identities. This is a pretty simple one. We just have a single term, cosine squared x, so we have an even power. The half-angle identity tells us that cosine squared x is 1 plus cosine of 2x over 2. So this is, I'm just going to replace that in the integral. I'm going to drag out this factor, this 2 that's in the bottom, I'm going to drag that out so it'll be a factor of 1/2 outside the integral. So I just have 1 plus cosine 2x. I've got two terms. We can split up an integral over addition. We're not raising the parentheses to a power, right? This is just to the first power. So I can split this integral up over addition. When I do that, both of the integrals that I write should have that factor of 1/2 in front. So I've got 1/2 times the integral of 1 dx plus 1/2 times the integral of cosine 2x dx. The integral of 1 we know how to do. The whole point of splitting up an integral over addition is I can approach them individually. So I know how to integrate 1. And then the integral of cosine 2x, well, that's one of those basic trig forms. I've got cosine of an angle, and here, if you wanna try this out before I say what I think, pause the video. But if we let u equal 2x, then du is 2 times dx. I need a factor of 2, and that's fine. I'm going to throw that in, and I'm going to compensate with a factor of 1/2 outside. So I've got 1/2 times the integral of 1 dx plus 1/4 times the integral of cosine u du. Now we know how to do both of these integrals, so let's go ahead and integrate. The function whose derivative is equal to 1 is just x. We're integrating with respect to x here, so we're gonna get an x expression. And the function of u, because we're integrating with respect to u, that has a derivative equal to cosine, the integral of cosine is sine. So we get sine u, and then plus a constant. Now I'm going to just put the 2x back in for u. We get 1/2 x plus 1/4 times sine of 2x plus a constant. If we had like a sine squared and a cosine squared multiplied together, we just use the half angle for both. If I had a cosine to the 4th, I'd use the double angle. I'd say that's cosine squared squared, and then we'd still use that half angle identity. Okay, so let's move on to secants and tangents. The strategy really involves just remembering our derivatives, right? Making the right u substitution is all about saying, oh, if this is my u, I could see its derivative show up elsewhere. So remember that the derivative of tangent is secant squared, and that the derivative of secant is secant tan. In addition, the Pythagorean identity, which we know as sine squared theta plus cosine squared theta equals 1. I can get another version of this identity that involves secants and tangents if I divide through by cosine squared theta. Then we get tan squared theta plus 1 is equal to secant squared theta. So we can convert even powers of secant to in terms of tangent, and likewise we can convert even powers of tangents in terms of secant. So if the power on secant is even and positive, we're going to save a secant squared factor. And when we pull out that factor and throw it at the end, the idea is that we're going to save that as our du. So if secant squared is our du, we want the rest of it as in terms of tangent. We're thinking that u is going to be equal to tangent. So I'm going to rewrite this first. I'm going to pull out a secant squared factor at the end. So in front I still have a secant squared of 3x times tan 3x times secant squared 3x dx. So I want the rest of this in terms of tangent, which means I want to do something about this secant squared that I have in the front. And I can do that with Pythagoras. So this is the integral of tan squared 3x plus 1 times tan 3x times secant squared 3x dx. So I've got the rest of it in terms of tangent. Now I'm ready for the substitution. We're going to let u equal tan 3x, and then we're going to find du. Don't forget about the chain rule. Du is 3 times secant squared 3x dx. That factor of 3 comes from applying the chain rule. So I need a factor of 3. That's fine. I'm going to throw that in. Compensate outside. Now I'm going to make my substitution. I've got 1/3 times the integral, in parentheses, u squared plus 1. And then here's another factor of u. And then at the end, there's my du. So again, everything matches up, right? This matches with this. This matches with that. And there's my du right there. Making a u substitution is all about accounting. Now we have this integral with u's that will be easier to do. We're going to do some algebra. I'm going to distribute this factor of u. So we have 1/3 times the integral of u cubed plus u du. It's a polynomial. Let's use the power rule. Using the power rule here, I get 1/4 u to the 4th plus 1/2 u squared, and then plus a constant. I'm going to do two things. I'm going to take this factor of 1/3 and distribute, and at the same time, I'm going to substitute tan of 3x back in for u. So we get 1/12 tan to the 4th of 3x plus 1/6 tan squared 3x plus a constant. Okay. Now, the other scenario that we can run into is if the power of tangent is odd and positive. Then we'd save a secant tangent factor at the end. So if we're saving a secant tan factor to be our du, that means we're thinking right out the gate that u is equal to secant, because the derivative of secant is secant tan. And if u is going to be secant, then we're going to convert tangents to secants using using Pythagoras. So remember we saw in the last example tan squared theta plus 1 is secant squared theta. So that means that tan squared theta is secant squared theta minus 1. So we're going to have that on hand. So they say, you know, save a secant tan factors. I'm going to start just by rewriting this before I save any factors of anything. I've got tan cubed x times, and then I've got a square root of secant x in the denominator. So that means I actually have up here a negative 1/2 power of secant. So if I save a secant tan factor, if I pull out a tan factor, I'm going to be left with tan squared. And if I save a factor of secant here, that means the only way that works is if I'm left with a minus 3/2 power of secant. Convince yourself, take a moment to look at this and convince yourself that these are equal. It's really just using the rules of exponents, right? So secant to the negative 3/2 times secant to the first does give us secant to the 1/2 because we have to add the exponents. So now our if we saved a secant tan at the end to be du, that means u has to be secant x So here is du. This is u squared. Oh, that's not u squared. That's tan squared. So I want to convert. I still haven't, if that's my du, I want the rest of it in terms of just secant. Okay, so I'm pretty psyched about the secant to the negative 3/2. That's just u to the minus 3/2. But I got to do something about this tan squared. And what I'm going to do is use Pythagoras to rewrite it. So this is secant squared x minus 1. Now I'll make my u substitution. So we have, if u is secant x, And in this first set of parentheses, I've got u squared minus 1. Secant to the minus 3 halves is u to the minus 3 halves. And secant tan, that's our du. So again, making a u substitution is just all about the accounting. I didn't need to throw in any constant factors. Everything matched up nicely. So again, it's not just a single term power rule, but it's something that I can apply the power rule to. It is a general power form integral, and we could see that after we distribute. Technically, it's not a polynomial, because polynomial is a term that applies when your power is only positive integers, but we could think of it like a polynomial in that the same approach, right? So it's still the general power form. We're going to use our rules of exponents. So if I'm distributing u squared times u to the negative 3 halves, adding the exponents, 2 plus a negative 3 halves is 4 halves, minus 3 halves is 1 half, u to the 1 half, minus u to the negative 3 halves, du. Now I'm going to use the power rule on this integral. So using on the first term, we get u to the 3 halves times 2/3, and then u to the negative 3 halves. If I apply the power rule, that'll be a u to the negative 1 half times a negative 2, plus a constant. So I'm going to put our expression for u back in. U is secant x, and then I'm just going to clean up that second term a little bit. So 2/3 times secant x to the 3 halves, and then this will be a plus 2 secant x to the negative 1 half plus a constant. You could leave it in this form if you like, or you could kind of go back to radical form. So this would be 2/3 times the square root of secant cubed x plus 2 over the square root of secant x plus a constant. Either is fine. Okay. So now, in a situation where we don't have any secant factors at all, and the power on tangent is even and positive, we can convert a tan squared to secant squared, again using Pythagoras, and then see where we're at. Then we expand, we kind of reevaluate. Sometimes we have to repeat this process. So we're going to see how it works here. And yeah, let's get started. So remember that tan squared x, we saw this in the last problem, tan squared is secant squared x minus 1. So the first thing, this is a definite integral. I'm going to just approach this and find the indefinite integral first. So I'm going to leave the limits off, and then once we figure out what this is as an indefinite integral, then we'll do the definite integral and we'll know what expression to plug the limits into. So the indefinite integral of tan to the 4th of x dx is, I'm going to write tan to the 4th as tan squared times tan squared. And this says just convert a factor of tan squared into secant squared. So I'm just going to take one of these. Maybe so this first tan squared factor, and write that as secant squared x minus 1. The second one, I'm going to leave that as tan squared right now. Maybe I'll want to do it again, but the idea is that I'm going to see where this leaves me. And then it says, then expand. So that means multiply it out. So we have the integral of tan squared times secant squared minus tan squared x dx. We have two terms. We can split up an integral over subtraction. So I'm going to split this up. This is the integral of tan squared x secant squared x dx minus the integral of tan squared x dx. The idea, the benefit to splitting up an integral like this is that I can approach them separately. And this first integral, tan squared secant squared, we can approach this because the derivative of tan is secant squared. So for this integral, we have a technique. We can let u equal tan x, so that du is secant squared x dx. The other integral, we have just an even non-negative or even and positive power on tangent. So we're back at the beginning here. So it says if there are no secant factors and the power on tangent is even and positive. Well, that's exactly the position we're in the second integral. So we're going to do this again. So sometimes you have to kind of repeat this process, but this factor of tan right here, or that term, I'm going to replace with secant squared x minus 1. And I'm going to hold off on making the substitution we mentioned there, and I'll do that in a second. So this is secant squared x minus 1. Now we can split up this integral over the subtraction. Be careful, when we split up that integral, we're subtracting the whole thing, so that will distribute. When we split this up, we're going to have minus the integral of secant squared x plus the integral of 1. And that's just because this negative here distributes. Okay, now I have 3 integrals. The first one we already mentioned, we have a plan of attack for that. We're going to let u equal tan x. So I'm actually going to make that substitution now. This looks like tan squared is going to be u squared, secant squared x dx, that's du, so that's a power rule integral, minus the integral. In the middle here, we just have the integral of secant squared x. But we know how to do that. In fact, this is just an integral we know. We know of a function whose derivative is secant squared x, and it is the tan function. So, so we can integrate that. And we know the integral of 1 is just x. So now let's integrate everything. We get 1/3 u cubed minus tan x plus a constant, of course. Now I'm going to put tan x back in for u. So I get 1/3 tan cubed x minus tan x plus a constant. So this is the indefinite integral of tan to the 4th x dx. Alright, so there's a preliminary result that we're going to use. Now we'll just remember that they in fact asked us to evaluate a definite integral. And I'm running out of room here, so I'm going to use my magic paper. So the integral from 0 to pi over 4 of tan to the 4th x dx is equal to, now I know the expression I'm going to use. I don't need to worry about the plus c because in the definite integral down here, so I'm going to take this expression, throw my limits on that. So plugging in pi over 4, 1/3 tan cubed pi over 4 minus tan of pi over 4 plus pi over 4. And then we're subtracting what we get when we plug in 0. 1/3 tan cubed of 0 minus tan of 0 plus 0. You can use your calculator if you want. If you need a reminder, or just looking at the unit circle, we could see that tangent of pi over 4, tangent is sine over cosine. So at pi over 4, sine and cosine are equal, which means tangent of pi over 4 is 1. If you want, you can use your calculator too. Just make sure you're in radian mode. And tan of 0, if it's sine over cosine, is 0 over 1. So you'll see that tan of 0 is 0. And so that means that this whole thing zeroes out. Tangent of pi over 4 is 1, so this is 1. This here is 1 cubed, which is also 1. So I've got, in the first set of parentheses is 1/3. Oops. Don't need the parentheses. I've got 1/3 minus 1 plus pi over 4. And I'm just going to simplify. 1/3 minus 1 is a negative 2/3 plus pi over 4, and I'll get a common denominator. Times 4 here, times 3 here, and we get 3 pi minus 8 over 12. And we can approximate that if we like. So 3 pi minus 8 over 12 is about 0.1187. So we have all these different techniques, right? Strategies to that will apply in different cases, right? Depending on what the integral looks like. And I should add, here's another case. Is that I guess another case here, if you're working with secants and tans, if these cases don't seem to work, right? If this 1, 2, and 3 cases, right, depending on what the powers are on secants and tans, if nothing seems to work, if it seems like you've got no options, you can always try converting to sines and cosines, right? Because secant is 1 over cosine, tangent is sine over cosine. And then see if one of our strategies for sines and cosines will apply.